Hi, everyone.
Hi, Arto. You can get going, I think.
Okay, so let's get started with the second part of reinforcement learning lecture. And I think this is the place where we roughly left off last week. So starting from here, Peter Bill briefly mentions the idea of learning optimal representations and how this idea is related to separation principle in control theory. So in classic control theory, there is a proof that we can learn separately like optimal estimator and optimal controller, and by combining those two, we will still get optimal control system. For instance, usually the optimal estimator might be a Kalman filter in classical control, and the estimator can be linear quadratic regulator, so we can compute the parameters of Kalman filter and of LQR separately, and then combining those two, we get like systems that is guaranteed to be optimal as well. So there are some theoretic developments in applying the same kind of paradigm of the same separation principle to deep learning, but we don't go into details on that, and I think it's more like a theoretical work at the moment rather than practical. All right, so with that, we move to discussion of end-to-end learning of representations, and we will discuss the idea of learning representation that are particularly good for planning. So some results in this direction were presented in this paper, again from this Berkeley research group. So the idea is that we can use a convolutional neural network to implement this value iteration network. So the value iteration network will take the representation of a state and the reward signal as an input, and is designed in a way that it is supposed to estimate the values associated with the state. So we will go into detail with that. So here we have this couple of slides that are meant to say that we don't really need to reconstruct, to do the reconstruction in pixel space to get the best system for planning. So we will look at what they propose to do, right. So here is this idea of value iteration network. We have this observation, and we send this observation to the value iteration module, which can be thought of as a recurrent convolutional computation. And the intuition behind it is as following. So first, I should probably introduce the value iteration idea. That's very like a basic idea in reinforcement learning. And imagine we have like a simple tabular reinforcement learning where we have a finite set of discrete states, and we can associate a value with each state, depending on how likely we are to get a reward starting from that state and following some policy. So by iterating this, like recurrently updating value for each state, we will converge to the actual values for the states in that system, and essentially what we do, we like iteratively refine the values for each state, and by doing like a number of these iterations, it's proven that we will converge to the actual values of the state, and then we can use these values to decide on the actions. So we will move towards the highest value state. Okay, but we cannot directly apply this to problems with high dimensional state space or continuous state space. So the idea of this paper is instead of doing this tabular value iteration, we can achieve something similar by applying convolutional computations, and the input here, you can see that it is like this grid having for each location we have some reward and a previous value. Then we apply this convolutional computation to obtain, we have some action space. So here you can see we have like 4 channels, which would correspond to 4 actions. Then we will do maximum pooling over these channels, and that will get us the values for the corresponding state. And by doing this computation recurrently, we are supposed to achieve the same effect as by doing a value iteration. And then we can send this values to some controller to produce a policy, right? So that will, so we can use these values to inform the policy. All right, so that's the idea. And the next idea, which is like a similar one. So this recurrent refinement of the values is, if it's done without actual interactions with the environment, it might be thought of as a planning. So we are planning on the MDP, which means we are so here the planning step would be a step of refinement of this value estimates for the state. So here we have this similar idea, which is called the universal planning network. Again, we take an observation, encode it into some latent representation, then we do a number of steps, and we are supposed to arrive at some goal state, and here it's so here it is not a reinforcement learning, it's like an imitation learning framework. We are given some expert produced trajectories and we learn this action sequences to imitate the expert. And the thing is here that this planning sequence is differentiable, so we can backpropagate through this sequence of actions. We have here have this forward dynamics model, which takes action and latent state and produces next latent state, and the goal is to achieve the final latent state to be similar to the encoding of goal state. Right, so in this way we can learn this kind of planning network in differentiable fashion by optimizing this planning objective. And again, this is done iteratively. All right, so yeah, so the idea here is that we improve our regular reactive imitation learner. That's kind of a neural network that takes, for example, we take current observation, we have a goal observation, and the network is supposed to predict the action given the action that will take us from the current state to the goal state. And the learning is done in this supervised fashion by imitating the expert provided actions, right? And this autoregressive imitation learner is improvement over that, because in this case we have this iterative refinement, so we can plan over so here we can only optimize a single transition, right? So we the pairs of states we expect those to be achievable in one step, but here we can optimize over the sequence of actions. So and that makes sense because actually what we want in our system to learn is a sequence of action, like a plan to achieve the goal rather than a single transition. So this allows.
Я ничего не слышу. Да.
Okay. All right. So yeah, the sequence of action. So we optimizing over the sequence of action, and this may provides better results. And they experimented with a number of tasks here, where this robot is supposed to grab a target object, something like that. And this approach demonstrated a solid improvement over this compare the baselines, so a reactive imitation learner, autoregressive imitation learner, those shown here, and this UPN, which is here, right? Yeah. And you can see that here we cannot outperform the expert because we are learning to like imitate the expert action, and they done some experiments here. So the number of planning steps, as we increase the number of planning steps, their results improve. And also you can see that this UPN planner performs better with more planning steps, like learns faster. And here, this plot, it demonstrates basically the inference time. So by increasing the same training procedure is applied, but by increasing the number of planning steps, we get better performance. And another application of this framework can be to provide the learning signal for reinforcement learning agent. So what we did before was imitation learning. We were just trying to reproduce the actions or trajectories provided by expert. But now what we can do, so we have learned this representation and transition models, and we can use this UPN to provide better shaped rewards for the reinforcement learning agent. So as we discussed last week, reward signal, natural reward signal in the environment might be sparse, and that makes learning difficult sometimes. So here we have this representation of the goal state, and we have the next state, and we can use the distance between the state, this observation at t+1 and the goal observation as a reward signal, and therefore we make the reward, we produce a dense reward signal which will inform the agent like how close the agent is to the goal, and this allows like a richer learning feedback for the agent. And they experimented with this, and they showed that the UPN representations can be used to like solve tasks with higher and higher complexity. I think they had some, in the papers they had some plots showing that without this UPN, this 5-link problem wasn't solved at all, but using this UPN representation, they were able to solve this 5-link problem. So that's like the approach, and how we can use representation learning for planning. So next, I think last time I mixed things up a bit. We have discussed this curl paper somewhat. previous time, but we will go over some of the details here once again. So we have here this plot showing the difference between learning from state and learning from pixels. So in this DeepMind control suite, we can run the reinforcement learning agent as by providing states as input. So we will have like this low dimensional representation of a state of the agent, or we can do it by feeding the raw images as a visual representation of a state. And as you can see, this D4PG, so this is a distributed policy gradient algorithm. It can achieve similar performance with when learning from pixels, but it requires much more data. So here you can see that the number of training steps is huge, while the learning agent that learns from states basically just can solve the task almost right away with much less transitions needed to learn. So to tackle this problem, we discussed this paper somewhat last time. So this is the curl paper, and it combines contrastive learning with reinforcement learning. And it's quite simple, but very efficient. And here, so SimClear was the state of the art at that moment, but I think there were a number of improvements in the space of this unsupervised learning in vision. Yet, so they show this typical contrastive learning architecture. We have an input image, we construct the augmented version of it, and then we maximize the agreement between these two predictions. And we discussed this in details a couple of months back. So yeah, this is done using this contrastive learning objective, and here it can be like we can use cosine similarity. There are other similarity measures, some variations of this objective as well, but that's not very important. So here again they show the importance of data augmentations, and some augmentations are shown to be more important than others, and cropping was the most important one. Okay, so the idea is to apply the same unsupervised learning approach to reinforcement learning. So we like jointly run reinforcement learning and contrastive unsupervised learning. We use the same kind of framework as used for unsupervised learning, but also we run the reinforcement learning on top of this encoding of the image input. And they discuss some modifications they've done here. So one important modification was using bilinear interpolation instead of cosine similarity. So that's cosine similarity does not have any parameters, but what they use here instead, they use this bilinear product of query and the key vectors, and in the experiments they show like a huge boost when using a bilinear product. Yeah, it's called differently in different papers. Distmult is another name for it, and I think it has shown some benefit in many tasks that rely on this like distance measure. I think in the recommender system it is used as well sometimes. So, but that's just another way to encode the similarity between two vectors, but you add some flexibility here. So, but also it obviously comes with some extra computational cost. And another change they made in comparison to Sinclair, they used momentum encoder as in Moko paper. And again, the momentum encoder demonstrated substantial benefit to the performance of in the reinforcement learning application. And yeah, I think we discussed this in some detail earlier. And again, we have looked at this plot, and it shows that in 500,000 transitions, curl almost matches the soft actor critic that learns from state. So that's a great performance in this case. Yeah, and with less transition, so it still requires more data, but I guess the data efficiency is improved substantially anyway. And but there are some tasks where there is a gap between the performance of this curl versus soft actor critic from state. And yeah, so they show that for some hard tasks, it is very far. So for here is a number of environments where learning from images doesn't perform that well. And again, we have discussed this table before. So so again, this curl application shows best performance in 5 out of 6 tasks here. Yeah, but apparently it doesn't work that well in this cheetah run environment. And yeah, so probably some environments, some like visual dynamic is harder to grasp for this kind of environments. And yeah, again, they show that they show that in some of these hardware environments, this approach might fail. And yeah, again, here you can see this learning curves shown in gray is learning from state, and curl in red. And yeah, so the gap is quite significant on these tasks. But as well, you can see that different approaches, like trying to learn for these environments from pixels, failed before as well. Yeah, and yeah, they talk about this improving the data efficiency, and specifically when talking about data efficiency, we are trying to achieve something close to human learning efficiency. And here you can see they are using 100,000 frames from Atari games, which corresponds roughly to 2 hours of playing. And I guess human can learn to perform quite well in these games within 2 hours. That's why it was they chosen this number of frames as a benchmark for data efficient learning. Yeah, and you can see how the score improves 5 times, but still you can see that this is 0.24 of human normalized score. So the scores achieved by this learning agents are still much lower than what was produced by humans. Yeah. But a significant improvement compared to what we had before. And now we can look at this table. They show percentage compared to the human normalized score achieved by algorithm. And you can see that in some games, it performs almost as well as humans. But in other games, the performance is really poor. So only 2 out of 9 games were going well in this case. Okay, and before switching to the next topic, we can talk about, let me see, no, that's not this one, this one. So just to continue on this topic of achieving human level data efficiency, this paper, Mastering Atari Games with Limited Data, also co-authored by Peter Abil. And in this paper, they managed to achieve superhuman performance on this 100K Atari benchmark. So, what they done, they essentially combined mu0 approach with contrastive learning. And you can go into this paper for details, but I will try to do a brief overview. So this paper relies on Monte Carlo tree search, this similar to mu0. So what is done? We have an observation. Then we encode this observation into some hidden state, latent representation, and then we run this state transition model in or latent dynamics model to unroll the trajectories. And we use the results of this Monte Carlo tree search to inform our decisions. And in mu0, this representation and latent dynamics model learn only from the reward and policy prediction and next state prediction signal. So the learning signal for to learn this representation and dynamics model is sparse, and therefore mu0 is extremely data hungry, and yeah, the performance was quite good, but it requires a lot of data. And yeah, so here are some details about the mu0 approach, but we will focus on particularly on the representation learning and what it has to bring at the table here. So the authors identified 3 challenges associated with mu0, and one of those challenges is the lack of supervision signal for environment model. And they proposed to use self-supervised consistency loss to address this problem. And instead of learning from this sparse signal or maybe scalar signals like predicting reward, the action, and like a next state, they use this self-supervised consistency. So we have observation at time step t and observation at time step t+1. We encode both observations using the representation model, and then we compute, given some action and the state representation, we compute the next state using this dynamics model. And this framework is inspired by Sim-Sayam framework for unsupervised learning in vision. So we have here this projector and predictor modules, which are just MLPs, and the gradient is backpropagated through one of these passes. So you can see that gradient is not backpropagated through the path where we represent actual next observation. So we use this one as a supervision for the other one, and in this way we can learn both representation and dynamics model end to end, and in this self-supervised fashion. Right, so they had another two other substantial improvements, but I think we shall skip those, and I will post a link to the paper, and there is also a video by Yannick Kilchner that explains this paper in a nice way if you're interested. But let's look at the results. Here you can see that this approach, again, we are looking at the results on this Atari 100K benchmark, and you can see that no of the baseline approaches outperformed human. You can see that the combined scores. So human is 1 here, and this efficient zero achieves 1.9 for mean and 1.09 for median score compared to human. So yeah, so this approach outperformed humans on the data efficiency on this benchmark. But again, you still can see that it doesn't achieve the best results across all of the environments. In some games, it is still outperformed by other approaches. But like so we still cannot say that. Yeah, so this is the algorithm that will work always the best. And yeah, but in some cases, the performance is much better. But you can see, for example, this private eye task. All reinforcement learning algorithms are far off the human, so some tasks are still unsolved, I guess. Right. And they have some other ablations here. For example, they compare again on this deep mind control suit, and so in 2 out of 3 tasks, you can see that this efficient zero outperforms soft actor critic learning from state. So that's kind of good performance. And again, they compare on this 100,000 transitions. So on the other hand, I have looked at the Atari benchmark on papers with code, and still, so this efficient zero is nowhere to be found on this leaderboard. So I think they presented only the results for 100,000 transitions, but the leaderboard is kind of indifferent to this number of transitions. And I don't know, maybe if you run this efficient zero for more steps, you will outperform some of these models, maybe not, but authors did not present anything in that direction. So yeah, still there are open questions, like again, relating to the question Srinivas asked last time, if this yields a benefit in final performance, not only in data efficiency. You can see that oftentimes there is no comparison in that direction. So, all right. With that done, let's move on to the next topic, and we will discuss another important problem in reinforcement learning. So before, we mostly discussed this data efficiency and related issues, and now we will talk about the exploitation trade-off. So to learn efficiently, the agents need to explore the space of possible actions in some way. And what is often like the simplest approach to this is like epsilon soft policy, and that would mean we will take some random actions with some small probability, and in simple like low dimensional and small environments, this can yield nice results, but in some more complex environments, it's quite hard to achieve good performance with simple exploration strategies. Some trajectories that can be good, but require like to do something that contradicts current policy at some stage, might never be explored with simple exploration strategies. So let's discuss now how the what is often done in these tabular cases. Again, something more, a bit more interesting than this epsilon soft random exploration. There are count-based exploration methods. And so we will count the number of visits into some state, and we can compute the confidence associated with those like how confident our policy is about certain state or state action pair based on how many times we visited that state or took that action from that state. And yeah, so there is an approach called UCB, upper confidence bound action selection, and there are a number of variations of it, but here is like a simple formula to represent it. So we select an action based on this Q values. Q value corresponds to the like value of state action pair. So like the estimate of the return we expect to achieve from that state taking that action. But we, when selecting an action, we add this confidence component, and we have here the logarithm of number of steps in the nominator, and number of times the action was taken by so actually we saw the outcome of this action n times, and again, when this number is small and t is large, we will get a large bonus, this exploration bonus. So that action will be more likely to be selected and therefore explored. So I hope that makes sense. And yeah, that's like a popular approach to exploration, but it's not directly applicable to the to the environments with more complex state representation. So taking that intuition, we can apply it to the more complex environments. And one of the ways was presented in this paper. And here the authors trained pixel CNN to estimate the, like they trained the pixel CNN to represent the input, and then they used density estimate from pixel CNN as a replacement for count. So if the pixel CNN has high confidence for some image as a visual representation of a state. Then we visited that state many times, that state or similar states. So in this way, we want to, this to be generalizable. So Pixel CNN will output, even if we haven't visited this particular state, but visited some similar states, Pixel CNN will still produce a high score for it. And if we haven't seen states that are similar to the one we observe now, it will have a low probability for that state under Pixel CNN, and therefore we need to explore that state more. All right, so that's the first approach, and something similar was done, but using the variational autoencoder and hashing to apply again this count-based exploration, but now we use variational autoencoder to hash the inputs, and then we count the number of times we visited a state that hashes to the same bin, as you can think of it, right? And therefore, similar states will be embedded in a similar way by variational autoencoder, and therefore they will be hashed into the same like bucket, and we can convert that into the count and apply the same approach that was so this UCB and the variations of UCB that is used in tabular methods, right? And again, they show here that this exploration bonuses provide a good boost to the performance of the agents. So they learn quicker, and in some cases, you can see that, for example, for this Montezuma revenge, TRPO was not learning, but when you add this exploration bonus, you can make it work. And here is the same, I think, for half cheetah environment. So next, all right, so this variational information maximization exploration. In this case, the idea is environment can have some like intrinsic uncertainty about it, and instead of so sometimes so we can use like confidence in predicting the next state as a measure of exploration, like, right? So if we can predict the next state well, then the state is well explored. If we cannot predict the next state, then the state is not well explored. But the problem is that some of these transitions are like highly uncertain intrinsically. So the environment is stochastic and the transitions are stochastic. So instead of using this predictability of the next state, in this paper, authors proposed to use the difference, basically the information gain from observing this transition, rather than like the quality of prediction itself. So if we have some prior, and then we observe the transition, we update the posterior, we get the posterior, and if posterior is like much better than the prior, then we got a lot of information. Therefore, we got to explore this state more, because we have we don't have a lot of information about this state. So that's the intuition behind this approach. And the next idea is this curiosity-driven exploration. And it's, again, it's a pretty nice idea. So let's have a look at this diagram. And here, the approach here is to learn both forward and inverse model. So inverse model, given current state and the next state, the inverse model is trained to predict the action that leads from this state to the next state. And therefore, this model basically learns only the relevant, the stuff that is relevant for predicting this previous state from the next state, right? So the forward model would only learn this information that is relevant for predicting next state. Therefore, a noise will be ignored by this learning procedure, right? And then we can use, again, the same kind of confidence in predicting the next state as this curiosity reward. So we add this reward for exploration, for curiosity, as a bonus alongside the extrinsic reward that is produced by the environment. So we have some reward that is specific to the environment, and then we add this exploration intrinsic reward signal that is produced by this curiosity module, right? So here you can see that the intrinsic curiosity reward is produced as a difference between the predicted and actual states, next state. So, and what they also tried, they tried to train agents without any supervision signal. So without any reward signal, they've managed to obtain the interesting behaviors. For instance, driven by only this curiosity-driven learning, they've managed to, I think, they managed to do something like 10 levels, 10 levels in a Mario game without any reward. So just by incentivizing agent to explore more. So that's pretty cool, I guess. All right. Yeah, so that's how can we use this.
Hey, Arto, I have a question here,
Sure.
or that occurs to me, which while this on the surface seems very, good, as I understood your explanation, even curiosity-driven is underlying it is the metric of information gain, that there is less information gain then you explore that state more, correct?
Yeah, yeah. So maybe let's.
So in that sense, isn't that the reward that it is seeking? It's just a different name for reward, right? I mean, a reward is a result, and you're seeking the result of less information gain versus a reward that the game gives you. So it seems somewhat, I mean, while, you know, it's a nice name to give it of curiosity-driven exploration, but at the end of the day, you're just choosing a different reward. Isn't that another way of looking at it?
Yeah, yeah. So that's, I think, what you described is quite correct. So we just managed to get a reward from the, like to construct a new reward for the agent without getting any extrinsic reward from the environment. So yeah, that's right. So we reward the actions that result in more, like in higher information gain, right? And I think there is something similar in humans. Again, there is some research in this direction. Like we have this in our brain, this signals. Often, I'm not sure if that applies to children, but adults are often very uncomfortable when exposed to situations they never been before, you know, and often humans hide like their ignorance in some areas, and I think that is like a sign of or byproduct of this mechanism in humans. We have in our brain this mechanism that pushes us toward knowing about possible situation we may end up in, right? But also
I mean, it's you know, there is this famous saying, right? In the mind of the beginner, there are lots of possibilities, but in the mind of the expert, there are very few.
Yeah,
right?
But
because
I guess
you have kind of pruned all the paths that you potentially think do not lead to the reward, but the reward is kind of fixed in your mind, whereas there's also this whole concept of intrinsic versus extrinsic rewards. And you can kind of think of it as this methodology somehow tries to bring in, if you consider that extrinsic rewards are the rewards that the game imposes on you, then this methodology somehow looks for intrinsic rewards, which are not the rewards that the game imposes on you. It's rewards that you seek out, which are different and which are information-based than the rewards that the game has chosen to give you.
Yeah. But also in like neuroscience and psychology, there is this idea that in human, actually, there are no extrinsic reward. All the rewards that we obtain from our environment are converted into intrinsic reward by our dopamine circuits, in a way that if something is rewarding, but you are used to this reward, you will not learn more from it. So this diminishing returns, and so nature was quite clever, I guess, in designing this reward circuits in our brain and the learning mechanism in our brain. And I think we still not there with the reinforcement learning. yeah, but yeah, that was a good point. And yeah, if you like think about it a bit more, it makes a lot of sense, this curiosity-driven approaches and stuff. Nice. Let's now move to other ways to how we can boost the exploration in reinforcement learning agents. So there is this goal GAN, and the idea here was to train a goal condition policy, and therefore boost the exploration by like generating the rewards. And the training is, we have this kind of curriculum learning by generating more and more complex rewards or goals, not reward, but goals. And so what they do here is they say that we continually retrained the GAN to generate goals of right level of difficulty. And yeah, that's kind of another take on it. And similar results here. Again, this imagined goals. So the training is done by generating some goal state and training to achieve that state. And again, we just yeah, so the agent can explore the field of possibilities by trying to achieve different states. And finally, we get to this another topic. How can we apply representation learning in a different way to learn to explore? All right. So here the representation learning is used to replace again. So how the exploration is often done? It's often we have some randomness for the exploration here. So, and here they present the idea of how can we use the prior knowledge to explore in more efficient way. So we let's first it will be more like supervised learning for exploration. So we have some latent exploration space, and yeah, so we inject this exploratory noise not in the action space, but in some latent space. And then we use this latent variable to produce behaviors. And the approach here was we have some discrete variable which correspond to a task. Then we encode this discrete variable into a latent variable z, which is like sampled from normal distribution. So, and then we use this as input to the policy together with the state. And we have some mutual information regularization in a way that we want to maximize mutual information between variable z and the trajectory. And in this way, the z will learn to represent each kind of behavior or each task specifically, so different tasks will be distinguishable here. All right, and here again another variation of this is this model agnostic exploration with structured noise. We again have some noise, but this time we sample not from a normal distribution or standard normal distribution, but from a normal distribution parameterized by mu and theta, and we learn it in such a way that so we update this means and standard deviations in a way that we achieve good performance. So we have many tasks, we have this multitask agent, and therefore to achieve good performance on multiple tasks, we need to encode some information about the task into Z. We can, we operate in the same maybe or similar environment, so the state might be the same, but depending on the task we need to take different actions. Therefore we will encode the information about the task into the latent variable. And so some experiments here were like yeah, so the experiments here showed that instead of just doing random stuff, the agent explored meaningful behaviors and achieved good performance quicker compared to other approaches here. Yeah, so this blue lines here are the approach shown here. And yeah, and again, these are kind of simple tasks, but for example, we have this ant robot or wheel robot, and the rewards are distributed in a special way that they are encountered here on this like semicircle. So it doesn't make sense to explore other areas too much. We just need to explore this semicircle. And here again, there were some blocks, and the usual task was to move the block into some goal. And instead of doing just random stuff, the agent was already kind of understanding that probably I need to move the block somewhere rather than, you know, trying all the meaningless things. So in this way, we can transfer the skills from one task to other tasks by encoding different behaviors in this latent space and then exploring through the possibilities of meaningful actions, the actions that were useful for tasks that we encountered before. But again, you can see that this relies on the fact that the previous tasks were somehow relevant to the new task, right? And if that's not the case, and we don't have a Z that corresponds to the new task, it might be problematic, I guess. But that's an interesting way to encode the prior knowledge for the agent. All right, and the last topic we will discuss now is unsupervised skill discovery. And there are a number of papers, but the approach is very similar. So the idea is to, again, you can see that this framework is similar to what we discussed before, but before we had multiple tasks and we learned to associate Z with a particular task, to learn to impose a structure on this latent space in a way that like each Z kind of corresponds to some of the tasks. But what we will do now, we will just maximize the mutual information between Z and some trajectory. And in this way, the agent learns like distinguishable behaviors. Yeah, so their experiments was just, so this time we don't have any goal. We just generate some trajectories and then we optimize Z in a way that we can kind of reconstruct the, yeah, so we train the model in a way that we can reconstruct Z from trajectory. And therefore, we kind of make this these meaningful. Yeah, and you can see that here this cheetah learns to run backward, run forward, and even to do some kind of backflip or something with in unsupervised fashion. And yeah, so that is expected to be useful for future tasks. So yeah, let's have a brief look on this variational option discovery paper to make it maybe more concrete. So all right, so the idea here, we have what they call here context, and here it's denoted as C, and in the slides that was Z, but doesn't matter, we have some latent variable. Here they name it context and denote as C, and we want to maximize the probability of C given this trajectory, while also yeah, we also have this entropy regularization term, which is introduced here to make sure that so this again introduces some amount of exploration. So we don't want our policy to be too deterministic. We want to have some entropy in the policy. We want to have some uncertainty in the policy as well. And yeah, so that's the way we learn this meaningful latent space. So this context generator, we sample, yeah, here is this like simplified version of this or minimal version of this algorithm. We have some policy, parameterized policy and parameterized decoder. The decoder takes the trajectory and reconstructs this context that was used to prime the policy to produce this trajectory. And yeah, so we update the decoder to optimize this objective, and we update the policy to maximize this equation. Right, so that's unsupervised skill or option discovery, and I think they also speak about it, that this can be later used in hierarchical reinforcement learning framework to compose more kind of more complex behaviors. And yeah, that's in a way it's also similar to this like novelty maximization, right? Right, I think we are done with this lecture, and yeah, again, it presents a lot of ideas, and maybe for more for more information, it's advised to check out papers, and there are also a list of additional papers that were not covered in this lecture. So it has a lot of references and broad overview of the topics of representation learning and reinforcement learning. And I think that was pretty nice, but also like maybe quite intense lecture in terms of like information density. So thank you for following.
Thanks for going through that, Tato. That was very interesting. At least the space seems very dynamic and vast.
Yeah, but also this reinforcement learning, yeah, at least to me, it looks like, yeah, there is a lot of uncertainty there still, and it's hard. Sometimes it's hard to figure out what works best, and also often there are a lot of like hyperparameters to tune to make this work for, and if you choose the hyperparameters in the wrong way, it doesn't convert, the learning doesn't converge. And also, as you can see in this paper, there is a lot of variance like between runs and also across the tasks. Yeah, so that's a very interesting field, and I think it will be developing in the nearest future.
Yeah, it seems, you know, if you were to think of the comparisons to image NLP or something, I think there hasn't at least yet been kind of convergence to certain kind of most commonly used methods which yield results, although that may not be true for specific things like the Atari games you talked about and stuff. Maybe in each domain, it's somewhat reduced, but it seems, you know, the domains are so different and variable and stuff, and that it's still a very dynamic and fast-moving and vast field. So it's not like,
and also
there's a lot more happening.
A lot of like dimensions of variation in benchmarking. Like, right, for example, mu0 performs quite well across a wide variety of tasks, but also it's really data inefficient, and therefore it's quite hard to compare. So not many like people or even research labs can afford training something like mu0 on many tasks, because it requires a lot of compute. Yeah, but again, that's quite interesting, and hopefully it will be developing alongside with robotics, and maybe more like if once reinforcement learning has more impact on the real world, it will get even more attention, and the research will speed up, because as you can see right now, most of the results are from like a couple of research institutions, like this like big reinforcement learning group in Berkeley. There is DeepMind, OpenAI, and yeah, I guess that's it for like top research institutions, at least in if you judge by the count of the papers produced by them.
Yeah, and I don't know whether it is, self-selection bias by the Berkeley guys, but I would have thought that given the history of robotics in CMU, that they would have also had quite a impact, but it doesn't, at least, I don't see as much, because they have a very strong, they were upfront in robotics long before any of the other guys showed up. Many years back, even in the 80s and 90s, way back. But correspondingly, I don't see in the combination, as you're saying, of reinforcement learning and robotics, I would have expected them to be very prominent, but I don't see as much output coming from there. I'm sure there is, but it doesn't quite seem to have the same visibility.
Yeah, I guess there is also like this so maybe we need to merge the control theory and reinforcement learning to get something, because as I heard it, like most of the real world control systems are very simple. Like you can solve most of the practical tasks with something like a PID controller, and then you can, if that is not enough, probably you will use something like ILQR, and yeah, but again, that is possible when operating in this kind of constrained space of tasks. But if we want the robots to like solve more complex tasks, probably it might require something more more similar to deep learning, but again, maybe there is some kind of gap between robotics from the point of view of like constructing robots, and then robotics and reinforcement learning applied to robots doing something. And yeah, I think a lot of research now, it seems like a lot of research now is done in simulators, and yeah, as far, for example, this Boston Dynamics, right, famous with their famous robots,
Right.
Dog-like creatures, they are focused on at least like a couple of years back, they were focused on the mechanic part of things, right? And I believe they announced like some collaborations with researchers to put more brains into that, like more logic into their robots. But I'm not sure where it's moving now, as they were acquired by Hyundai, I guess, or something. Yeah, but yeah, like who knows what will happen in like a couple of years.
Yeah. Okay, I think that brings us to the end of this whole journey on unsupervised learning, which has been a long one, almost more than 7 months, I think, or more. So thanks for sticking with it and helping us get through multiple presentations, and especially the last 4 lectures, Arto. And I think this is the final session. Thanks everybody for joining, and I'll post the recording and post the links to all of the recordings as well.
Yes, thank you for organizing it. A really cool course. It's definitely one of the like more intense ones, but
Yeah,
I guess it was the effort.
yeah. I think at least several of the concepts seem to be very foundational to a lot of things, like the whole pixel CNN and unsupervised learning in images, video, and then that seems to be taking off in other domains as well. So definitely most intense, since it's directly, I think, for a graduate level course, exposing people to state-of-the-art research. But thanks for helping us through it. Okay, great, everybody. Thanks for joining. I'll post the recording shortly. Bye.
Bye, guys. Take care.
Goodbye, everyone.